have seen that a given semigroup right? How to construct a convex set. Let me denote that one as like, well, that's not correct actually. Convex set S with a given choice of half space. And the one thing to remember is that SM is strongly admissible if and only if this convex set is actually convex body that is compact. So today we will see how to attach a convex set to a given algebra, and the key idea is the conversion from algebra to semigroup by a given choice of valuation. So let's start with the definition of valuation.
By the way, is there a notion called abelian semigroup or non-abelian semigroup? Because if you semigroup is a set with summation of addition, right?
Yes.
And then whether this is commutative or not, because you are considering everything in Zn.
So
it's a commutative, right?
Yes. So as far as I know, semigroup is always additive. However, there could be semigroup which is not a subsemigroup of lattice. So this kind of semigroup, which is the subsemigroup of a certain lattice, called affine semigroup.
Yeah, but also it is possible that
of course
A plus B is not necessarily equal to B plus A, right? I mean, semigroup is just a set.
Yes.
With addition,
yes.
Associativity of the addition, and then it's closed under.
Right. I haven't seen any use of
Other.
Right. So the definition of valuation. Okay. Setting. Okay. So A is algebra over a field K. So you can think about just the number of complex numbers. And a gamma is an ordered, totally ordered abelian group. So means we are there is a total order on gamma, which respects the addition, which means if A is less than B, then A plus C is less than B plus C for all C in gamma. So again, you can think about just a lattice Zn, and that's just lexicographic order. Okay. So a gamma valued valuation on A is a function A but exclude the zero element to gamma such that it satisfies the three axioms. So it respects the multiplication. So V of F times G is V of F plus V of G, and scalar multiplication. And the third one is V of F plus G is at least minimum of V of F and V of G, where if F plus G is non-zero. Yeah. So example. So say X is a smooth, X is just a curve. And just to choose a smooth point. On X. And let's take A as the field of rational functions. So you can just see X is just the complex line C, and P is just a origin. And you just consider all the rational functions with one variable. Right? So then I define V of F as the order of F, the vanishing order of F at the point P. Then this is a Z-valued valuation. So suppose F has a power series with the initial power is 1. This one has initial power 1, but then you have a minus, then the order will be greater than minimum. Right? So any question about this definition?
Vanishing order 1 and vanishing order 1.
So what I'm saying, yeah. So X is just C and P is the origin, the point 0. And say I have x2 square, then G is say x3 is minus x squared plus x to 4, then F plus G, the V of F plus G is 3.
Okay, is that the bench? Okay, that's right.
Yes. Okay. So the example we have in mind from the very beginning is actually algebraic variety and the field of rational functions on the variety. So what I'm saying is that this is a very basic fact. So any field F of transcendental degree So a field over base field K with the transcendental degree of F over small k is D. Okay, I want to keep N. Has at least one faithful valuation, Zn valuation, okay. Valued valuation. Faithful means surjective. Means that B is surjective. You can find this one, the Jacobson Basic Algebra, second volume, chapter 9. It's nice. If you have some extra time, it's nice to review the algebra. Okay. So now, so now here's the setting. F is again finite generated field with transcendental degree over K is N. And now you choose one valuation, Zn valuation, and for just the simplicity you just assume that it's faithful. And now we have an algebra graded, the subalgebra of Ft. The grading is just grading by the degree of T. It's a polynomial ring with one variable T with the coefficients from F. Okay. Now, from this valuation V on F, we will construct a valuation on A or F bracket T. Okay. So here's the definition. So what do I mean by constructing the valuation on A? So first I need a total order O, and I will raise this one, the rank of this one by 1. Total order on Z cross Zn. So the first extra factor will record somehow the degree, the grading. Okay. So here's the definition of the total order we will consider. So say n alpha and m beta is in Zn. Okay, so alpha beta are the elements of Zn. Please let me know if there's any ambiguity in my writing. Okay, there are lots of lattices. Sometimes I just use a vector notation by one letter. So if it's not clear, let me know. So we say n alpha. Okay. If n is, so Z comes with the natural ordering, the first one.
So you are trying to construct the valuation.
Yes.
Z times Zn value.
Yes. So, yes. we're lifting the valuation on F. So if n is greater than m, then we say n alpha is less than equal to, okay, let me choose this notation. Okay. Go to m better. And if n is equal to m, now you look at the left one. If alpha is less than equal to beta, then we just preserve the order. It's just a technical assumption choice so that the new valuation actually satisfies the last one. You may wonder, why do we reverse the order? So it just will be clear so that the last inequality is satisfied. Okay, now the function. So let me use this notation as a v sub t. So it's f t minus 0 to z cross zn. So an arbitrary element in the domain will have this expression, lower order term. So am is non-zero. Then the value will be, you just record the degree of p and just take the valuation of the coefficient, leading coefficient. So if v is faithful, so is this new valuation. Okay, so now we do the conversion. So obvious, right? So say if I have algebra, graded sub-algebra of ft, then you get a semigroup. It's nothing but the image of this A. Sorry, sometime A minus 0, right? Yeah. So in this notation, there is implicitly chosen V. Okay. So sometimes people write down V. So that's very important data here. So this is algebra conversion from algebra to semigroup. And here there's a natural choice of M, the half space, just upper half plane by this first factor. So let's choose M as just the half space such that the first coordinate is non-negative. Well, basically we consider the S of A, if you look at the image, the degree is always non-negative. So S of A, it sits inside of M. So we have a semigroup and we have a half space. So we get a convex set. Yeah. So that one is denoted by A. And if you want, you can denote that V as well. Okay, so that's the by definition. It's just the convex set coming from semigroup with this half space. So if I don't say what is the half space, it's just fixed as this one. Okay, so this is called Newton-Okounkov convex set. We don't know if it is a convex body yet. Okay, so this is Newton-Okounkov set by definition. All right. So please remember the first application of this assignment of convex set was that the description of the asymptotic behavior of the Hilbert function of the semigroup. So now we want to talk about the Hilbert function of graded algebra. So obviously we want to have the Hilbert function of algebra is preserved or completely described by the Hilbert function of the semigroup. Any question? So we are done. So we are done. We know what is the Newton-Okounkov convex set of an algebra. Okay. Okay, I want to keep this one. Yes, so it's a proposition 227. Okay, again, if this is from the KK, the reference KK. If you want to see the more details about proofs, please. Well, this one we will see the proof. So we want to claim that the Hilbert function of the semigroup is actually equal to the Hilbert function of our original object A. The Hilbert function of A. It is not always true. That's the thing. We need one extra technical assumption for the valuation. V satisfies the following thing, and we will find what to put it in here by completing the proof. So then it's H sub S of A. So this is the notation for the Hilbert function of a semigroup. So this is by definition the number of points of the semigroup on the level K. Well, let's use M. Too much K here. Okay, M. Okay, level M. Okay. So now look at the semigroup. So semigroup is image. So we only consider the first one is M. Right? V of AM. So this is the number of VT of F such that F is in M, the degree M part. So A is A is graded, right? So we can grade it sub algebra. So this is the direct sum of M part, but that is the same as LM is subspace of F. That's the definition. Okay, this is a polynomial with one variable t, so it's graded by like that. Yeah. So this is what I mean by AM. Okay, again, but this is Lm t to the m. Oh, yes. And by the definition, v sub t of f is m v of am. So f will be g times t to the m, and then g is in Lm, which is in f. So that is the same as number of v of g, such that g is in Lm. No. Okay, let's compare with Hilbert function of A. M. So when A is graded, by the definition, the Hilbert function of algebra is nothing but the dimension of the M over the field, the base field at K. So we want to say this is equal, right? So this is equal if the valuation V has this following property. If V has one-dimensional leaves, yes. So we need this expression here. So the Hilbert function of algebra is preserved if the valuation we chose has this property. Okay, let me tell you what this is now. Okay, so just aside for this definition, so we have valuation on f minus 0 to zn, or just lambda. So f, so if you, for alpha in zn, f sub alpha denote just all the elements in f. So the valuation is at least alpha or f is 0. So it's a vector space. You can see that we just define a filtration on f. Okay. Now the leaf above alpha, which is denoted as f alpha hat, is just f alpha modeled by union of all f beta, such that alpha is less than beta. This we are doing the filtration. We are chopping out off f. Okay.
F alpha is the valuation which value is greater than alpha, or f equals 0.
Right. So the valuation itself, the domain does not contain 0. Right?
Okay.
But we want to have a vector space, so we want to include the 0 in f sub alpha. So now, so here we say V has one-dimensional leaves if for all alpha in Zn, the dimension of this leaf is either 0 or 1. Okay. That's also the definition. So it jump by one dimension, or it doesn't jump at all. So here's a fact.
So F bar is a vector space is guaranteed by the definition of.
Yes. So suppose we has this one-dimensional leaves, and then for any okay, we start with F. For any finite dimensional subspace, when I say subspace, I mean real just K vector space. Okay, yes. So
F is a vector space.
So
F is the
F is a field. F is a field over another base field. Okay. Yes. So it's a finite dimensional subspace of F. And whenever I say subspace, it's K vector space. So I need a notation for that. So let me say that's W. Right. Then the dimension of W is actually the same as the cardinality of this image W. Okay, remember we don't consider 0. Yes. This thing we will go through examples. Okay, so let's write it as a record. So here, so if V has a one-dimensional leaves, the dimension of Lm is actually the same as the number of values. So here sort of we completed the conversion. So if you want to have a nice conversion, what I mean by nice is that the conversion preserves the Hilbert function. You need an extra condition on the valuation, and this is what we want. Well, it depends on what you want actually, though, right? So let's summarize. If we have a graded subalgebra of F bracket T, and you choose evaluation with one-dimensional leaves on F, then you lift one higher V sub T and take the semigroup and take the convex set. So far we get a convex set. We don't know if it's we want to have a compact, right? So before so here we know this, right? So if the semigroup is strongly indivisible, then we have this convex body, strongly indivisible, right? So strictly convex, right? So
how difficult evaluation as one-dimensional leaves?
So if my goal is to finish today's lecture by introducing this geometric valuation, and this geometric valuation is automatically has this property. So you sort of don't really recognize this property. They don't even say this. But this property is very important for this proposition. So in practice, somehow
it's all given. It's almost naturally given.
Yes. But of course, if you construct your valuation not geometric way, then and you want to use this fact, you have to check if your valuation has that property. That is important too, actually. Yeah. Okay, so that was the definition of these one-dimensional leaves. Now here's the theorem. 230. So if A is what is the English? Almost integral type. Okay, so from now on, let me use A for the graded subalgebra of F, the big F bracket T. So what is we have a small field, small k. You can think about this as the number of complex numbers C, and the big F is, you can think this one as a function field of variety. And now you think about this polynomial ring with the T, and now we have this graded subalgebra. You will see the example, specific example. But so if that algebra is of almost integral type, then always this conversion. Okay, remember that M. So usually I don't write down, but because the beginning, what is the half space? The A is strongly admissible. Therefore, the Newton-Okounkov convex set is a convex body. So don't worry about this of almost integral type. So basically all these famous algebras you will meet in algebraic geometry, they are this type. So you can consider Newton-Okounkov body if you start from geometry. Okay, so that's what I'm going to say, or maybe let's do this example before going into algebra again. Okay. So let's see if we can recover toric variety. So what was the original foundation of this?
The example for this is F. We just consider the big F as a function field of the variety.
Right. That's what we have in mind. I have in mind. So if your object to study is a variety, then the function field.
What is A then?
The A, so A could be a homogeneous coordinate ring attached to this variety with a given line bundle or something else. So that will be the second top. But before going into that, let's see this simple example. Let's recover the Newton Polytope to be familiar with this construction. Okay, so.
By the way, do you use the Hilbert function when you construct the Okounkov body? So what I'm asking is, do we need the assumption of one-dimensional leaves for valuation when we construct the Okounkov body?
No.
Body is defined without any.
Right. So that's the whole point. If your question has nothing to do with the Hilbert function of your algebra, but you just need some convex body, you don't need that. You don't need that assumption. Yes. But one of the applications Kava and Hovansky had was to show this polynomial growth of a Hilbert function for general algebra, not necessarily finite generated. Yes. So right. So when I just began this study, I tried to construct something. I wanted to show that this one is a nice one, but always it came from the very beginning of these papers. I always try to see if my valuation has this property. Well, whenever I construct something, actually I fail that even this proof, this one. So you have to be careful, actually. Yeah. Okay, so let's recover the Newton polytope. Yes, I want to compare these two approaches, KKs and LMs. Okay. And you will see how they are different and the same somehow. So recover Newton polytope of a toric variety. So there are two versions. I present very explicit one, like P2, and second version is just an abstract version. So let's start with a very specific one. So the simplest toric variety is P2, projective plane. You can think about P1, but let's do P2. Okay. So I will understand P2 embedded in P5 using this Veronese embedding. Okay, in this following way. So C star 2 is embedded into P5. Theta 1, theta 2 with the following monomials. So please let me know if you are not familiar with any part. Okay, so I will just draw like this. I'm drawing this triangle with these 5, 1, 2, 3, 4, 5, 6 lattice points. It goes to 0, theta 1 squared, theta 2, theta 1, theta 2, theta 2 squared. So this is the embedding of C star to P5, and just take the closure of the image, then that's just nothing but the Veronese embedding of P2 in P5. Yes, okay. So I'm looking at P2 as this closure of the image. Okay, let me put this one as phi inside of P5. Okay. So by the definition of the Newton polytope in this case, is nothing but the triangle we started with is actually well.
What is Newton polytope of a total drive?
So yes, there are many versions. So let me give you one, and I will give you another one later. Okay. So this is actually a general setting. It's a finite subset of. Okay, I just want to keep it Zn such that we have this map. So say I have A1 up to a big N. to p to the power big N minus 1. Now I'm just using the vector notation. Theta is mapped to theta A1, theta AN. Just do the same thing. Okay. Then the Newton, okay. Then the toric variety we consider is written as this, right? So this is the closure of the, so some people use this image of this. Oh, sorry. We choose a finite subset such that this is embedding. So we need injectivity, okay? Then the image, V of A is the toric variety. So this is, you can think this is a toric variety with a given choice of line bundle. So it's embedded into projective space.
That's one dimensional.
Which one is one dimensional? Oh, sorry. Yes. Yes. So some people use this like vector notation, but I will not. Okay, yeah. There are lots of line, overline, underline. So. Is this expression clear to you? Okay. So.
What is this?
Right. So A1 is a vector, right? A11 dot 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 A1n. Then theta to the power A1 is just the theta 1 A11 multiplicative. So this is just the characters of this torus. So I will say lots of things, so that maybe one of them you are familiar with. These are the characters of C star n. Right? So this one is the example. We have A in Z2, and we have embedding. Take the closure. That's just P2 in P5. Then the Newton Polytop. Newton Polytope of XA is nothing but the closed convex hull of this set A. So somehow this is very combinatoric. So later we will see some geometric expression of this one. So we want to realize this Polytope as a Newton Okounkov body.
So we need to take closure?
Yes. Oh, in this case it's always closed. Sorry, so maybe that's why you are confused. Yes, convex hull, it's finite set. So it's always polygon, actually. Polytope. Sorry.
So this any toric variety can be constructed.
Any projective toric variety.
Projective toric variety. So this is called the p-toric variety of A, or what? Just the p-toric variety?
Yes, it's the toric variety of A. Yes. Well, we don't. So the toric variety of, you can say, so it's coming from A. Or you can go backward. If we have a projective toric variety, what does? Okay, sorry. It's a projective toric variety, projectively embedded in projective space. So this is somehow special one, but it becomes just perfectly matching with the combinatorics. So if you have a toric variety sits inside of a projective space, you will see what A's are. So you will see the Newton Polytope again. So
if this is non-singular.
Oh, it could.
If this is non-singular, then it seems to me that there is a Polytope, isn't it?
I have heard of that. Yes.
So
Here, the key point is that yes, that's actually the point. Is
this is a simple convex polytope, isn't it? Is it n-dimensional?
doesn't have to be.
No, if it is non-singular, then this
Even moment polytope.
moment polytope, yeah.
You can understand that one as the moment polytope. So that one significance of this one is XA could be singular.
Yeah, XA could be singular, but the question is when. So if you choose A correctly, then you will get
Moment.
singular. And if this is a non-singular toric variety, then
You
you can view this as a.
it is the moment polytope for the Fubini study form.
Yeah, symplectic. So it is a Taylor structure,
Yes.
and then so this polytope has to be simple convex polytope, I guess.
If you want to consider this one as a moment polytope, I guess you need a non-singularity. Yes. Yes.
So then this A should be, if you make, then it should, this A should construct something like a simple means on each vertex exactly n facets intersect.
Yes. So that's the connection to symplectic geometry.
All right.
So here the point is that so if you're this one you can just take as a definition, and everything is combinatorics actually, right? You start from just a bunch of points in that, and you construct a toric variety as just the closure of this torus. So it is toric variety. So this one we just define as the Newton polytope. So, okay, there are lots of behind story. That's why we try to study other things because however, so for those who are too much, then just take this one as the definition.
So the question is, if you choose this point, you want to AN, and then it could be possible that Newton polytope inside, interior, there could be a point. Some of the point AI could be sitting inside.
Yes.
But if you drop it, you still get the same polytope, right?
Yes.
Then if you take out one point AI and you construct toric variety, maybe it is sitting in a smaller, one-dimensional, smaller projective.
Right. So it may not be embedding.
It may not be.
Embedding. That smaller polytope sort of is related to this one as a like projection. Yes. So you know when you.
But if Newton polytope is, if a Newton polytope is a nice shape, like a simple polytope, my question is, could it be still embedded, and then you can have different embeddings?
Yes, different embedding. Yes, but the very beginning you have this non-singular, so you have non-singular toric variety, and then. So what I'm trying to say is this is the thing. If you have A, and Professor said, I think you consider all the lattice points, then it's guaranteed that the embedding corresponding to all these lattice points always embedding. Okay, but you may just take out some of them. Still, it's well defined. Well defined, but may not be embedding.
But you still get the same Newton polytope.
You get the same Newton polytope for the original. So there's intrinsic understanding and extrinsic interest. Extrinsic and interesting. What am I saying? Extrinsic understanding and intrinsic understanding of a given toric variety. So when you have a simple polytope, you already have a toric variety which does not sit in any projective space. Now it depends on this mapping to projective space. If you use all the lattice points, you get a isomorphic toric variety sitting inside the projective space. Yes.
But out of just this Newton polytope, can you associate that with the toric variety, or what do you mean by?
Yes, if you have a Newton polytope, you consider all these lattice points. So actually, when you say the Newton polytope, A is already given. Yes, the Newton polytope is already given. Maybe your question, if we have this lattice polytope, can we consider toric variety whose Newton polytope is that one? Yes.
So which counts everything, all the vertices, the lattice point inside them.
Yes. Yeah, actually, there is a criteria that if not all, you don't have to choose all of them, but there's a criteria which if you choose at least some lattice point satisfying these, then you always get embedding. Yeah, at least the vertices you have to choose.
If you have two different embeddings, then are they isomorphic or?
Yes, it's two different embeddings.
No, but embedding is only for complete torus embedding, but you are taking closure of it, right? So you make it different.
I see the point.
Because toric variety is nothing but the complexification of torus. So you are just complexifying this torus in one way. Right?
Sorry, so I think what you are saying is I have a C star n at the beginning and I consider the embedding of a C star n using different A. Of course, then
you get different things.
Right. C star and inside they are all isomorphic, but yeah, that about
closure.
they could be all totally different, right?
So if you have same Newton polytope, but using what kind of this lattice point, you can choose different embeddings, right?
Embedding of C star n.
Yes.
Yes.
And then you get different polytope. Toric varieties with the same Newton polytope, I guess. Convex Hall of that, and this points. If you drop some points interior, you still get the same convex Hall. Am I confusing?
So there is a choice of A, which is discrete, and polytope is somehow compact.
Right. Yeah.
So I think you have to distinguish choice of A and the polytope.
Right.
So
Newton polytope plus choice of A gives you one specific toric variety.
okay.
But just the Newton polytope is not sufficient enough to determine.
So when you say Newton, a polytope does not really satisfy, but when you say Newton polytope, I think a priori you already chose A.
All these
Or some, but yes. Hopefully I understood. Yes. So again, we are very lucky to have this excellent book about toric variety written by Cox, Little, Shank. This is like Bible for the toric variety. So here you can see very careful study of this different choice of A and polytope too. Okay? So, okay, so let's go back.
The first coordinate in this should be 1 or 0.
Oh, thanks. Powers. Oops. It's 1. Yes. Theta 1 to power 0, theta 2 power 0. Thank you. So we will review lots of toric geometry during this, but so for now let's take this one as the definition and let's recover this triangle as a Newton Okounkov body. So what we need, by the way, what did I say? Okay. because I skipped the part. Okay, it's okay. Good. So what is the algebra? So the when I say Newton-Okounkov body, I mean Newton-Okounkov body of algebra. So here's this. So we consider just this space spanned by all these rational functions. Sorry, I'm using this notation now. Okay, this one. So this is a subspace of the field of rational functions of C star n. It's monomials, if you want. It's just the monomials just defined on C star n. But this C star n is open dense in this toric variety. So this is actually the same as the field of rational functions of this toric variety. Now I consider this algebra, which is
Zeta to the A capital N or span?
Span over C.
Yeah, but theta A1 up to index.
Theta of A1 up to. Thank you. Thank you. Yes. Or this. Okay. Consider this. And now we consider the subalgebra spanned by all these monomials.
As an algebra or?
No, it's vector space. It's a linear combination of all of them. And now you consider this algebra. Now you consider these polynomials.
The multiple, right?
You can think this is the homogeneous coordinate ring of toric variety inside of P n minus 1. Okay. So now we define the valuation. Just by theta of AI is defined by AI. This is the definition. So this is the generators. So you can expand this definition everywhere. And VT is there's a degree, there's a grading on AL. Okay, so these are degree 1 component, and if you multiply 2 of them, you will get degree 2 components as V sub T. Okay, so so what happened here? Okay, so let me just do step by step. So this one is actually the level 1 of the semigroup. Okay, so to get the Newton-Okounkov body, we have to get the semigroup, right? Semigroup. Yeah. So this one is actually so this one, if you want, so VT of theta AI. Some people put the T to say the degree, but this is actually just 1 comma AI. So let's think about let's complete the level 1 of the semigroup. So the level 1 of the semigroup is the values are all AI. Now you consider level 2, but it's just obvious. Level 2 is you multiply 2 of them and take the valuation, then that's the sum of these AIs. So you get a semigroup which is generated by level 1. And then take that closed cone of this semigroup and slice this one by this hyperplane at level 1. You just get this, what was the notation? This AL is nothing but the convex hull of A. So we recover this polytope. So now it's because you already so AL is nice. Okay, good. Okay. And please note that again, XA could be singular. This toric variety could be singular toric variety. Okay, so let's go back to the definition of this expression of almost integral type. Actually, I already brought this notation. Okay. So start from there.
There's something called
Sorry?
projective. I mean, you can embed Veronese embedding into the bigger projective space. And then instead of considering toric variety, you just consider. I mean, I don't remember. Veronese variety embedding is from where to where?
So if
Arbitrary.
so, suppose you have a projective space and you want to embed this one into bigger space. One way to do is that. So say this one has coordinate x, y, z, homogeneous coordinates. You consider all the monomials of degree, in this case 2. Well, degree 4. Then, so, okay, we have to, what is the, how many? X square, y square, z square. How many? 6, so P5, right? So that is called the Veronese I think it's V2, Veronese embedding of order 2, something like that.
So can't you do the same thing?
Yes.
For any projective variety?
Any projective variety.
Or
Projective space,
right.
yes.
That's wonderful.
Yeah, for projective space, yes. Yes. Actually, that's what this is just an approach of this embedding from C*2 view. Okay. Okay, so let's go back to the abstract setting. So F is.
If you have a projective variety, that means by definition you can embed this into some projective space.
Sure.
And then using that embedding, can you construct something similarly?
Yes, that's exactly what we are going to do. This just shows one example. So we can recover toric variety. I mean, of course, we don't have to do this one, right? I mean, toric variety is already developed. I mean, just one way. So there's toric variety, and we generalize, and we really want to make sure that we generalized it. And so it's a field with a transcendental degree over small k is, say, up to the n. Okay. Now choose L as finite dimensional vector space. So K vector subspace. I just realized. Okay, K dimensional subspace of F as K vector space. Okay, Whenever I say subspace, I really meant that. Okay, so here, well, what is this? So in this setting, this is our F, and small f case you can consider the field of rational numbers, and I chose L. Bunch of rational functions. Okay, so here's this notation A sub L. So this is direct sum of L, M, T, M. M is this natural number. So now you can consider this one as sub-algebra of Ft, where Lm just a vector space spanned by this product of m elements of L. Lm is a vector space spanned by Fi, Fm for some I'm saying L is monomials, and L square is just vector space spanned by the product of two monomials, and L3 is the space. Just one way to say this degree component.
This one is F1 times F, 2 times M.
Spanned by, yes, product. M of them.
I1, Fi.
Yeah, the N.
I1, Fi, M might be better.
Yes, M product.
Right.
Spanned by all the products of M elements. Yes. So, well, here I didn't put T to the M. Just T, this part, I just want to record the grading. Okay. Okay. So any algebra is called integral type if A is finite generated as AL module for some L. Okay. And A is called almost integral type if A is it's sub algebra of a certain thing which is integral type.
So A is a K module or what module?
As A sub L module.
So any A sub L module is called integral type?
Yes, it is.
Finitely generated.
Yes, any AL is integral type. Yes, because it's generated by AL. So just generated by one. Yeah.
So when you say A is of integral type, and what do you start with A? Is A algebra? What kind of?
Yes, sorry. I always say A is a sub-algebra of A is a graded sub-algebra of this. Sorry.
Okay.
Yeah. If I don't say anything further, it's all coming from the very beginning. The notation just we keep using. Okay. Yes, roughly speaking, A sub L is recognized as this homogeneous coordinate ring of a certain projective variety like that. And integral type, this one is related to a certain choice of very ample line bundle on the projective variety. And almost integral type is that you choose a line bundle which is not necessarily very ample line bundle. So this says any algebra we encounter in this geometry, we get a Newton-Okounkov body. I think it's good to stop here. So if you have time, just try to be familiar with the definition of Newton-Okounkov body, and next time we will start with this geometry, starting from algebraic variety, and then think about all this algebra coming from algebraic variety. Any questions?